Everybody, this is Dr. Harmon, and yesterday I was pretty dissatisfied by the lecture period. We had some technical glitches. I couldn't log in to Vital Source, and it was just a Monday, and so I really was not happy with how that kind of came out. So I've decided I'm going to do. This will be an extra or supplemental screencast for the one that I'm going to do tomorrow, which would be Wednesday, the 3rd of April. And I also realized that as I've built the schedule for this spring, I've incorporated these cases from the Foreman text, and they're pretty complicated, as well as we're starting to move into some more complicated material there in the Anderson text, in other words, in the management science. So I wanted to just simply say, okay, I'm going to add the equivalent of probably at least of a third lecture period, which you can see on demand, to make sure that we can get covered in class what we want to get covered. Now, I prefer to spend the live time talking about the DataSmart case, and that's the one involving the one that's going to be involving it's over in chapter 3 of Foreman, and that's the one involving Mandrill, where we build a predictive model. And so I want to spend the classroom time on that on Wednesday. So I'm going to cover single arbitrary. Now I have a key over there for it. And as you'll notice, the naive Bayes, that's the one this is the Mandrill case. It's due on Friday. Single arbitrary is due on Friday. And so I wanted to go ahead and do this case, single arbitrary, the one out of the Anderson text, and to talk about it. Now, if you go down to Module 10, you'll see that I have the key, and that's what I'm going to go over today. But I also want to spend some time. And then you also have the Burger Dome case. That's it's called single in the chapter 11 student file. So you have two cases coming up. You've got the single arbitrary this week, okay, and then you've got the Burger Dome case next week that deal with queuing theory. And I wanted to go ahead and make a supplemental broadcast for this, okay? So I'm going to be a little more didactic than usual, and what I want to do is cover some of the material up to that case, and then open it up and take a look at it. Now, this special supplemental screencast, I'll post it over there in the announcements section. It may run more than 50 minutes, so if it does, that's fine. Watch what you want to, or watch it in chunks. You know, we have a Friday lab time that's a virtual lab, and this, I guess you could say, kind of qualifies for that. So I hope that's making some sense to you, and we'll go from there. I want to start just by giving us some of the conceptual background, and this is over in chapter 11, where we talk about waiting line models. When we talk about a waiting line model, we're also talking about what we call queuing theory, and that is, how do we handle people who come into an establishment, or people who come in to, say, use a machine of some type? How do we handle how long they wait to be served, and then how that impacts how long we actually provide them the service? And so we get a sense of how long that person has to spend in total. And you're used to you're used to queues and waiting lines all the time. You drive in to get food, or you go to a restaurant and you sit, or use an ATM, or any transaction is going to involve that. So chapter 11 starts us with the simplest type of waiting line and moves us on from there. So I'm over here, I'm in the textbook. This is the Anderson text. and it gives us just an overview of the chapter. And I think this is a good way for us to get started by just taking a look at the various types of waiting lines that structures are out there. And we have what we call a single server waiting line, okay? Then we have multiple servers, okay? And then we start to move into things like arbitrary service times, finite types of waiting lines, Poisson and exponential service times. So we'll take a quick look at each of those. And so I'm going to go ahead and move on over here into over to the next pages. Okay, so this gives us the contents. And let's move on over. Okay, and here in the textbook they talk about the queue or the queuing theories, and they talk about Erlang, and he was a telephone engineer, as the text states, and he tried to study about the congestion that gets created when people would all use the phone. None of you remember this, but there was a day and time when on holidays, like Christmas, Mother's Day, Easter, that if you didn't make a phone call the day before, you probably would call and literally your call would not go through because the lines would be jammed with phone calls. And this is before the phone systems went to automated systems that could handle the switches and the call volumes. So he tried to come up with some rules and some guidelines about waiting line theories, about waiting lines, and he came up with this idea of what we call the operating characteristic, and they're all outlined here. First, number 1 through 6. Notice something, okay? That you'll see the word average time, the phrase average time pop up, average units, and then you'll also see probability. So as I mentioned in the lecture yesterday, this involves probabilistic thinking and using probability to understand how likely it is someone will show up to be served, okay? And then how long do people have to wait for service? Now, if I'm not mistaken, I had put and here they are. I had provided you some resources to take a look at that will help you understand how important this idea is. I'm not sure if we have any marketing majors in the class this semester, but I can tell you this. You definitely want to be cued in on this, because the longer people wait to be served, the more likely it is they'll go somewhere else. They'll basically switch brands or switch facilities. And so I have some resources here for you. The ROI and analytics, but these two are really important. Is why we won't wait. It's dealing with customer satisfaction and profits, and how long will people wait. And we have some fairly good ideas of queuing line theory and how long people will wait to be served. Okay. So I want you to take a look at those, those resources there, and to give you some more background in addition to what is over here in the text. Now, the authors always like to give us some examples, and one of the things that I cannot emphasize to you enough is that management science is a very practical piece of your business education. It may be the most important because it draws on a whole set of elements. It draws on your understanding of your function that you've been trained to, be it accounting, finance, marketing, at the same time, it deals with business situations it deals with problems or situations that are operative at the retail level and at the wholesale level or distribution level and at the manufacturing level and even really at the extraction level. Okay, so it's management science is eminently practical, and we've understood that by taking models, we can build a mathematical model, we can simulate results, we can look at what results will look like, and so forth. Well, here's an example from the ATM waiting line. And this is important because they talk about the structure of a waiting line, and they talk about a single server line. And this is figure 11.1 is really something that it really puts into, this is a model, and it puts into perspective what we're looking at. And so we have our system, our business, and how we serve people. And somebody walks in the door, somebody calls us on the phone, somebody goes to our website, okay? And they come into a waiting line, okay? Now, if it's Amazon, you go in and the waiting line is almost non-existent, primarily because of two things. First of all, if you're going into Amazon, you're not there for the same thing everybody else is. So that gives Amazon a great advantage, or any e-tailer. If you're calling in, say to talk to somebody at Rocket Loans, okay, or Quicken Books, that's a different critter, because you start to move into dealing with people. And then if you walk into a restaurant, I think the point's pretty clear, and the diagram is very clear that we have a customer, and then they have a waiting line. All right, and this can even pertain to things like electronic commerce or e-tailing. If you log in and then you want to get some help or advice, and you have somebody who'll have a chat function, and they get to you quickly or they do not. Or maybe you call for help at an 800 number to say, gee, I'm having trouble with this product, I need some help. Then we have the order filling. We take care of whatever that need is, and then the customer leaves after the order is fulfilled. This is the simplest of all queuing. This is the simplest of all queuing models. Okay, and we walk through the probabilities for these distributions, and they talk about using the Poisson probability function. And what the Poisson fits well, it's the best model we have for waiting lines, because it assumes there's an inflow of customers, then things kind of plateau, and then there's another inflow of customers, and then things kind of hit a plateau. This is going to be very evident if you're working in a company that does batch processing. Maybe they manufacture components for a product. Maybe they assemble a product, or in a restaurant, or you're in an insurance, you're in company, and people call in or they email you. And so we have a way to compute the arrival rates, and then we start to compute the probability that someone will come in, and they're showing here during a 1 minute period. They show us here for the this will be applicable to that Burger Dome case, where they talk about the probability of the number of people who arrive during a 1 minute period, and then the distribution of service times. And notice here we're using exponential values. Okay. And the authors give us some good side notes in understanding it. The math here is not as important as you grasping those issues. Now, it has some things like Q discipline, and that could be first come, first serve. So whoever shows up first at the line at Six Flags gets to ride on whatever ride you want to get on. Then we have a thing called a steady state operation. And what that means is we kind of are operating with activity builds up and we get things done and then we hit a steady state. In other words, that system has people to take care of and those people get taken care of. And so we're back at a steady state. And here's the single server waiting model, okay, with the Poisson arrivals and exponential service times. They walk us through the probabilities again of that type of situation. Now, this will walk us into the Burger Dome problem, and we'll take a little bit of a look at that next week. So I want to pop us on over to page 525. And this is the single arbitrary. They're going to give us this. And there are different mathematical approaches to this. And this is a single server waiting line model with Poisson arrivals. In other words, we kind of build up and plateau, and arbitrary service times. And they walk you through some of the notation about that. And here we have the arrival rate, the service rate, and the standard deviation of the service time. And so again, you see we're looking at using probabilities, average units of time. And this is the single arbitrary. This is the web file. That's the one that we're using, going to work on. And they talk about a model where we have random arrivals, but constant service times, okay? And so they'll begin to walk us through the question here of the issue of the assumptions for the model, then its operating characteristics, and let's look at the single arbitrary case and we'll talk about it some. Okay. Now, what I asked you to do was to use goal seek to obtain the service cost per channel. Now, and then I asked you to assume that the waiting cost was $1.16, and you want to get a total cost per period of $2.99. So let's stop and think about this for just a moment. This looks suspiciously like a total cost model, okay? The waiting cost could be considered a variable cost. When we're operating with an assumed Poisson arrival rate, in other words, people come in at random, but it is a build up and then level off, build up and level off. That's like a variable cost. It's the cost of the waiting line. The cost is going to vary in terms of the number of people that we have. Then we have the service cost per channel. Now, if we assume, okay, that we have a set service cost, i.e. a fixed cost, Now we then have the elements that give us the total cost per period, per time period. So it looks very much like that. Now you'll see here the operating characteristics. But let's talk about a couple of things. First of all, the arrival rate. Okay. The service rate and the standard deviation of the service time. And we're given those figures. Now, let's go back up there for a moment and take a look at the text. And we'll go back here for a moment. And we get the operating characteristics for getting the customers through the system. Okay, and that's the arrival rate. Okay, then we have the service times. And we got the arrival rate of the percentage of those in terms of the number of minutes that we figure we'll have as they come in. And we get that arrival rate on the basis of using a probability. And they show us that, for example, down here, this seafood supply place, this is at the bottom of the page here, okay? They have a 21 customers per hour or 0.35 customers per minute, okay? So let's go back and look at this. There we are. Same times for service rates. I'll go back and take a look at it again. And they have a standard, and there's a visit here. They talk about a random variable with an average of 2 minutes per customer. And this is the service rate, the number of customers per minute. And so that walks us through, and then the standard deviation of that time. Okay. The thing to understand is this: the math is nice, but what you've got to understand is we scale, okay, during our arrival rate, how many people come in the door within a given period of time? During the service time, what percentage of the rate are they served? And then what's the standard deviation of the service time? And then we walk through this issue, the probability there are no customers in the system, the average numbers of customers waiting, and notice how we calculate all of that. The average number of customers in the system. And notice how we're taking that ratio there, B7 over B8. Same story here. The average number of customers in the system. The average number of time as a customer spends waiting. We've got that W, and how much time they spend in the system, period, and the probability that somebody has to wait. So if you go back to that model 11.1 we looked at earlier, we're trying to see how that type of thing works itself out when we have a single arbitrary. We have a single channel, one customer at a time, and we have arbitrary service times that we basically say, okay, the service time is X amount of minutes, period. So that lets us calculate the waiting cost per period and the service cost. And what I asked you to do there was to use the goal seek to obtain the service cost per channel, assuming that the waiting cost per unit is $1.16. And then you assume you want to obtain a total cost per period of $2.99. And again, you're going to go back up and I ask you to use goal seek. Okay. And we assume that we've got the service cost, so we want to set the sale, the total cost per period, to $2.99. So here, and we want that to be 2.99. And we're going to do that by changing the waiting cost. We're going to do that by changing the service cost per unit. Well, we want to obtain that, so we're going to assume the waiting cost. So let's do this, and we're going to be looking at the goal seek. And I want to set the total cost per time period to 2.99. And I want to change the cell, okay. And we have the waiting cost per unit is 116. So we're going to change the service cost per channel. And we'll run it. Now let's say, for example, that I wanted to make the total cost per time period less. Well, I can do that. I'm going to use the goal seek. And I'm going to set this cell, and I want to reduce it down to a total cost per time period. Now remember, one of the ways that we handle costs with queuing theory is we mimic waiting time as a variable cost and service time as a fixed cost. And we end up then with the total cost per period. So I'm going to set that to, I'm going to make that $2.50. I'm going to go up here and I want to find the service cost per channel. And let's see what we do. If we can get a solution. And we do. And what we see is we reduce the service cost per channel, okay? The total cost per time period is $2.50. Notice that we've reduced the service cost by basically, from the other optimal solution, it was like 89 cents. So there's almost a one-for-one trade-off for the service cost. And we'll cancel that. We'll go back. to our original case. Now, again, as they walk us through, and I want to show you this, this is where they get these figures. The probability that no customers are in the system. All right. And we take PO and we divide that. That's 1 minus 1 minus, and we'll go back over here to the arrival time. Okay. And the service rate. And this gives us the probability, and 1 minus that, the probability that we won't have anybody in the queue. And that's that first. Notice it's B7 over B8. Now notice we get the average number of customers in the waiting line. And let's look at this for just a moment. We're working with B7, the arrival rate, squared, times 2. And that's going to be times B9, which is the service rate, which is the standard deviation. The standard deviation, of course, that's going to be squared, so that's actually the variance. And then we're going to take B7 divided by B8. We're going to take the arrival rate divided by the service time. And that's going to be divided by 2 times 1 minus the arrival rate divided by the service rate. So you can see we're working these ratios. I'll go back over here to the text to get the probability that we won't have any customers. And we walk through the rest of these, the average number of customers in the waiting line, average number of customers in the system, the average number of time that they spend in the waiting line, average number of time, the average amount of time my customer spends in the system, and the probability that an arriving customer has to wait. So put the math aside for a minute and think through logically with what they're telling us. The first thing we want to know is, what's the likelihood that we won't have anybody in the system? Well, it's roughly about 30%. And it's 1 minus the arrival rate divided by the service rate. Now remember, we're talking about probabilities. So we're taking 1, which is the sum of all probabilities, and we're subtracting the probability of an arrival rate divided by the service rate. And that gives us that difference. Then we move looking at average numbers of people who are in the waiting line, the average number of customers that are in the system. So we get some people in the waiting line and some people being served, and the amount of time a person spends waiting, the average time that a person spends in the system. So this average time a person spends waiting and the time they spend in the system tells us how much time in total they're going to spend. And then we go back to this, the probability that an arriving customer has to wait. And that's going to be the arrival rate divided by the service rate. Then we get our cost, a waiting cost per unit and the service cost per unit. You say, well, what do you mean waiting cost? What's waiting cost? Well, let's go back over the text for a moment and talk about what we mean by waiting cost. The whole idea is this. Waiting cost can occur in a couple of different ways. One, it means you have to build a facility of some kind to house people. An airport's a good example. People don't just stand outside and get on an airplane. They go into a warehouse called an airport. If you have to maintain a queue, say you're at Six Flags, there's a cost imposed. If you're talking about someone calling in to place an order or talk to you, there's a cost imposed if they decide to leave. There's also a cost imposed to keep them on hold. And that's why I have these two resources here. Service times we can master pretty well. Those are controllable kinds of things. Waiting lines are not, unless we choose to actively manage them. And you can see, we can look into, put in that people may choose to go somewhere else if the waiting line is too long. And the best example is you go to eat at a restaurant, you ask how long is the waiting time, and they say 45 minutes. And you have to make a decision. Well, I wait 45 minutes, or do I go on down the road and go to eat somewhere else? Now, as you notice, and as I had mentioned already, service cost and waiting cost add up to the total cost. Now, we've talked about concave and convex functions that are different from just the linear assumptions we've been working under. And notice that the total cost is the sum total of the waiting cost and the service cost. So as I mentioned before, it mimics the total cost model very, very carefully. Now, over here on page 523, the authors give you an interesting insight in all this by talking about the waiting cost. Now, I've talked from more of a decision maker, practical operating process, but take a look at what they have here. Waiting cost is based on the average number of units in the system. It includes the time spent waiting in line plus the time spent being served. Okay? So if I'm wanting to make a certain level of profits, I've got to be able to run enough people through there that I actually generate business. People who are waiting are not, they're people who are waiting for our service are people who have money in hand, ready to pay, ready to use the service, but we're not ready to take care of them to meet their needs. And so this single arbitrary model, we see how it works. And I talked about that in class Monday, some about using a car wash where you pay a certain amount and you get a certain amount of time with the machine, okay? And we want to diminish the waiting cost. The more I push this back, the waiting cost, notice that service cost in an arbitrary or a generalized, the service cost is linear. But this is not a linear process because I've got a concave, pardon me, a convex total cost curve and waiting cost. And here we see, here's the optimal point for waiting cost. Here's the best, this is the best intersection of service and waiting costs. And then of course, then I have the total cost. If I can move this back, I move the waiting costs back to the left, I'm going to reduce the total cost. If I move the waiting cost to the right, the total cost will move up. The service cost is fixed. Now, one of the things we can do is lower the service cost. But here, of course, we're assuming it's linear, and so it stays constant. And we tried the best we can to keep service costs constant so that there's more than just a cost involved. This is also a customer service strategy. If people know what to expect, then they're more likely to trade with you or to buy your services because there are no surprises for them. If your service is erratic, your costs are going to go up because you're either going to have to spend more money on material or more money on people or more money on space or some combination of the three of them. Okay? So again here, we're just going to use goal seek to try to obtain, to see what our total cost per period is given our operating characteristics, our arrival rates, and our standard deviation of service time. Now I'm going to do something here, and I'm going to change the standard deviation of service time to 1.1. Now let's see if anything happens. And boy, does it. When I reduce the service line, notice the average number of customers in the waiting line goes down. I'll pop this back up. You'll see. Let's say I can get this down even more to 1.05, and let's see what happens. And the average number of customers waiting goes down. Notice this. And the number of customers in the system goes down. And the average time a customer spends changes. So we can play around with that. And that is the standard deviation. We use the standard deviation there for a very simple reason. Okay? Along with the average. The standard deviation is going to tell us how much fluctuation there will be. So if the average time a customer spends being served is 5 minutes, and then the standard deviation is 1.5 minutes, then it's going to run somewhere from between 6.5 minutes back to 3.5 minutes. And obviously, with an operating characteristic, the bigger the standard deviation, the bigger these numbers become, and the more variability that gets introduced into the system, and the more issues we have. Now, I'm going to do this. I'm going to write down, let's see, we've got these figures here, all right? And I'm going to say, all right, let's just see what happens. We'll experiment a little bit. Let's take this down to 1.1. All right. And let's go down and notice that my total cost per time period has gone down, because I've introduced more discipline into the service time. If I put this down to 0.95, you can really see what happens. Now, the probabilities that people are in the system stay the same. The probability that somebody has to wait stays the same. The average number of customers is the same, but our total cost per time period has gone down. Okay. Now, the authors also spent some time talking about the economic analysis of these lines. And of course, that's where they put in the total cost approach. And we'll look at the Burger Dome case where they talk about, do we need more than one server? And we can use this model to determine if it's worthwhile to use an additional server. Okay? Well, I think we've covered what we would need to cover. See if there's anything else. The general relationships waiting line, the model. And table 11.4 is a pretty valuable tool. Okay, and here you're looking at the ratio, okay, of the customer and the time spent per minute. And we look at the number of servers. These are multiple server lines, and we'll talk a little bit about them some more next week. And the Burger Dome will be a little bit more will be a more complicated case. But we started with single service, single arbitrary today. And that was over here on page 525. Okay. Well, this is going to be posted in the announcements, and I will say this is a supplement for Wednesday's screencast. All right. And then we'll focus on Wednesday, we're going to focus on the mandrel case out of the foreman text. So I'm going to stop the sharing.